Optimization problems. Here we look at how to solve problems of optimization. Optimization means that we are either maximizing something or minimizing something. So here we have some general steps. First of all, you need to understand the problem. So in this step, you need to read the problem carefully until you understand it. Ask yourself, what do you not know? What is given? And what are you looking for? Secondly, if you can, draw a diagram. It's not always possible to draw a diagram, but many times it is. And diagrams are extremely helpful in helping you understand the problem. Introduce notation. Make sure you define variables and your function that you're trying to maximize or minimize. Oftentimes, the function that you are trying to maximize or minimize, which they call Q here, will be expressed as a function of more than one variable. If this happens, then you must reduce the number of variables to a single variable. Oftentimes, this can be done by asking, what do you know about the relationship between the variables in the problem? And lastly, we will use the methods that we learned in previous sections to find the absolute maximum or minimum value. The best way to understand optimization problems is to just do some examples. So let's take a look at our first example. Here it says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Now here I have a diagram to show you. Here we have a river and we're making a rectangular fenced-in area. And we're calling the length of this side X, this side is also X, and this other side we're calling Y. And the area refers to the space inside the rectangle. Now, you don't have to be given a drawing. You could always make your own. And all you would have to do is draw a river, something like this, and then set up your rectangle next to that river. And you can define the variables in the same way. Now, I like the picture that I have here, and so I'm going to go ahead and use this one, but it's not hard to set up your own diagram. The first thing I like to do is ask, what are we trying to optimize here? And if you read the problem carefully, you'll see that it says, we want the largest area. So this means that we are trying to maximize the area. So the first thing we need to do to maximize the area is ask ourselves, in this problem, what is the area of this rectangle? Now we should know that the area of a rectangle is one dimension multiplied by the other dimension. And in this case, that is X times Y. So I will write area is equal to X times Y. And then I like to abbreviate things, and so I'll just refer to the area as capital A. This is the function that we are trying to maximize. Now, the problem here is that this is a function of two variables. We have an X and we have a Y. So what we need to do now is ask, what else do we know about X and Y? What is the relationship between X and Y? And if we read the problem carefully, it says a farmer has 2,400 feet of fencing. Now, if you want to get the largest area, you need to use all of the fencing material. The fence runs along this side, and this side. So we know the total amount of fence here is 2,400 feet. So in this diagram, what we know is that 2x plus y must be equal to 2,400. So x is 2x, plus y is 2400. And now that I have a relationship between x and y, I can solve for y very easily by simply subtracting 2x from both sides. And now that I know that y is 2400 minus x, I can take this expression for y, come back up to the function we wish to maximize, and substitute that expression in for y in that function. And so our area function, which is x times y, now becomes x times 2400 minus 2x. And now you see the area is expressed as a function of a single variable. And so area here can be simplified to 2400x minus 2x squared, if we multiply that out. And if I wish to maximize the area, I know I need to take the derivative of the area with respect to x, which is 2400 minus 4x. And if I'm looking for a maximum, I'm going to set that equal to 0 and then solve for x. And in this case, this is really simple to do. When you solve for x here, you're going to get x equals 600. And if x is 600, y, which is over here, is 2400 minus 2 times 600. And that is 2400 minus 1200, which is 1200. So we suspect the dimensions to maximize the area are 600 and 1200. But we have to check to make sure this actually is a maximum. Because when you take a derivative and set it equal to 0, that is the technique for finding maximums and minimums. So how do we know this is a maximum? Well, let's put x equals 600 on our number line, and let's take a look at our derivative dA dx. If we plug in a number larger than 600, let's say I pick x equals 800 or something like that, then dA dx is 2400 minus 4 times 800. And the important thing is that's a negative number. So our derivative would be negative there. And if I pick a number less than 600, like let's say x equals 400, if you plug 400 in here, 2400 minus 1600 is positive. So what we know is the derivative of the area is increasing and then decreasing. And when this happens, if a function is increasing and then decreasing, you have a maximum at this number. So now we know the dimensions that maximize the area are 600 feet by 1200 feet. In our next example, a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, so we're going to minimize the cost. The cost is directly associated with how much material you use to make the can. So over here we have a can that has been taken apart. You can see we have the top of the can, the bottom of the can, both of those are circles of radius r. And then if you cut the side of the can open, you can see that this has a circumference of 2 pi times r and a height of h. And so the amount of material to make the top, the bottom, and the side of the can is what we call the surface area. And I'm going to call that S. And the surface area of a cylinder like this is going to be the area of the bottom plus the area of the top, and so that is pi r squared plus pi r squared, plus the area of the sides. Now, if you lay this out flat, you will get a rectangle, and the length of that rectangle is 2 pi r, and the height will be h. So the surface area is 2 pi r squared plus 2 pi r h. And this is the function that we want to minimize in this case. Because if you want to minimize the cost of making a can, you need to use as little material as possible. Once again, the problem with this function is that it has two variables. It has r for radius and h for height. So we have to ask, what else do we know about r and h? Well, it's actually in the first sentence. It says this cylindrical can is to be made to hold 1 liter of oil. How much a can holds is its volume. And the volume of a cylinder, which I will call V, is pi r squared times h. And we know that the volume in this case is 1 liter. Now, a small detail here. I'm not going to use 1 liter. I'm going to use 1,000 cubic centimeters. And that is because 1 liter is equivalent to 1,000 cubic centimeters. The reason for this is because if I'm going to measure R and H, those will not be measured in liters. Those will be measured in centimeters. So I need to convert my volume measurement from liters to cubic centimeters. Now what I know is that the volume is 1,000. So I can substitute that in here for V, and doing so is going to give me 1,000 is equal to pi r squared times h. This is a relationship between r and h, because those are the only two variables in this equation. And furthermore, I can easily solve for h. All I have to do to solve for h is divide by pi r squared on both sides, and this gives us h is equal to 1,000 divided by pi r squared. And now, just like before, I'm going to take this expression for h and substitute it into the function that I am trying to minimize, which is the surface area. So if I do that, the surface area becomes 2 pi r squared plus 2 pi r times h, which is 1,000 over pi r squared. And now I'm just going to simplify this as much as possible here. So pi cancels out. This r cancels out one of these r's, and our surface area becomes 2 pi r squared plus 2 times 1,000 is 2,000 divided by r. And this is now the function that I wish to minimize. So to minimize this function, we are going to take the derivative of that function s with respect to the variable r. The derivative here is going to be 4 pi r. So just using the power rule, bringing the 2 down in front. 2 times 2 is 4 pi r to the 2 minus 1 power. And then 2,000 divided by r, it's helpful to think of this as 2,000 times r to the negative 1. So the derivative is going to be negative 1 times 2,000 times r to the negative 2. And so its derivative is negative 2,000 divided by r squared. And I'm going to set this equal to 0 to find out how to minimize it. Now, if we add 2,000 over r squared to both sides, we end up getting this equation. And then we can cross multiply. So 4 pi r times r squared is 4 pi r cubed. And 2,000 times 1 is 2,000. And I can divide both sides by 4 pi. And this gives us r cubed is equal to 500 over pi. And so r is going to be the cube root of 500 over pi. And just like before, we could check to make sure that this gives us a minimum. So we can put this value here on our number line, cube root of 500 over pi. And when you test to the left and to the right of that number, you will find that the derivative is negative to the left and positive to the right, which means the surface area function is decreasing and then increasing. So to minimize the surface area, we want to use this value for r. And then let's go ahead and approximate that. So plugging this into a calculator, we can see that this is approximately equal to 5.4, and this would be measured in centimeters. But if we go back to the beginning, it asks to find the dimensions that will minimize the cost. And this cylinder has two dimensions. It has r and it also has h. So we know what r is, but now we have to come to this equation here to find out what h is. And so we know that h is equal to 1,000 divided by pi r squared. And in this case, that is going to be 1,000 divided by pi times the cube root of 500 over pi, quantity squared. And this is a truly horrific number here. This can be simplified, but in the interest of time here, I'm just going to plug it into a calculator to get an approximation. And as you can see here, this number is approximately 10.8 centimeters. So the dimensions of the can is the radius is 5.4 centimeters and the height is 10.8 centimeters. And if you think about that, this is a very square looking can because this will be 10.8 and the radius is 5.4, which means the diameter is also 10.8. Next, let's find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So here we have a graph of a semicircle, and then we have a rectangle inscribed in it. So what that means is that two corners of the rectangle are on the semicircle, and the other corners are on the x-axis. Now, the rectangle doesn't have to look like that, right? The rectangle could be drawn more like this, or it could be drawn like this. And so there are lots of possibilities for how we could draw this rectangle. But we want to try to find the rectangle that has a maximum area. So notice how the point on the semicircle here is xy. And that means that this distance from here to here is x, and the distance from here to here is y. Now that also means the distance over here is also x, and therefore the length of this side of the rectangle is 2x. And you can see that they've labeled it like that in the picture. So now we know why that is 2x. So the area of your rectangle, which is what we mean to maximize here, is going to be the length 2x multiplied by the width y. Okay, so area is equal to 2xy. And as usual, I'm going to abbreviate area with capital A and just say A is equal to 2xy. And this is the function that we wish to maximize. But we can't do it, not yet, because our function A has two variables on the other side. We need to get rid of one of these variables. So as before, you know this is where we ask, what else do we know about x and y? Well, what we know is that the point xy is on this semicircle. So we need to remember, what is the equation of a circle? Well, we should know in this case that it's x squared plus y squared is equal to r squared, because the center of our circle is at the origin and the radius of our circle is r. So this gives us a natural relationship between x and y. Now, if you solve for y, you will get y squared equals r squared minus x squared. And then if you take the square root of both sides, you get y is equal to plus or minus the square root of r squared minus x squared. Now, why plus or minus? Well, because when you graph a circle, you get the whole thing. And so this is the equation of the whole circle. So the positive represents the top half of the circle, and the negative represents the bottom half of the circle. So in this case, we only need to concern ourselves with the top half of the circle, because that is the semicircle here that we have in the beginning. So this is what we know about y and x. And let's keep in mind that r is not a variable. R is a constant, okay? So r is just the radius of the circle, which would have been given in the beginning. And so this really is just an equation that has two variables, y and x. So now that I know y must be equal to this, I can take this and plug it into our function that we wish to maximize. And so our area function becomes 2x times y, which is the square root of r squared minus x squared. And now to maximize this, I'm going to take the derivative of a with respect to x. And to do that, I need to use the product rule. We have a product of the function 2x multiplied by this square root function here. So the product rule says we are going to take the first function 2x and multiply by the derivative of the second function. So let's remind ourselves that this is the same as r squared minus x squared to the 1/2 power. And so the derivative is going to be 1/2 r squared minus x squared to the negative 1/2 times the derivative of the inside. Now be careful here. The derivative of r squared is 0 because r is a constant. The derivative of negative x squared is negative 2x. So let's go ahead and fill all that in here. Okay, so that is the first function times the derivative of the second function, plus now we're going to take the second function, square root of r squared minus x squared, and multiply it by the derivative of 2x, which is just 2. Now let's clean this up. So we got a 2 here, cancels the 2 here, and this becomes negative 2x times x is negative 2x squared. R squared minus x squared to the negative 1/2 is going to drop to the denominator and become the square root of r squared minus x squared, and then plus 2 times the square root of r squared minus x squared. So this is what our derivative dA dx is equal to. And of course, we're going to set this derivative equal to 0. And I'll add this term to the other side, which gives us 2 times the square root is equal to 2x squared over the square root. And a real nice technique for solving this that I've already used before here is put this over 1 and then just cross multiply. So we're going to multiply these two things. And when you multiply those, it gets really nice. You get 2 times r squared minus x squared, because when you multiply these radicals together, you just get what is inside. And this is going to equal 2x squared, right? Because that's just 2x squared times 1. You can divide by 2 and cancel the 2 here. And so you get r squared minus x squared is equal to x squared. Now keep in mind, you're trying to solve for x squared, or x rather. So I'm going to add x squared to both sides, and that's going to give me 2x squared is equal to r squared, right, because these cancel out. And then I'll divide by 2. And finally, I'll take the square root of both sides, and that gives us x is equal to the square root of r squared, which is r, over the square root of 2. And you can also write this as r radical 2 divided by 2 if you choose to rationalize the denominator. So that is the value of x. Now we have to solve for the value of y, and we'll just remember that y, it's right here, was equal to the square root of r squared minus x squared. So y is going to be the square root of r squared minus this number squared. And this is equal to the square root of r squared minus 2r over 4, or 2r squared over 4. So just a little detail here, I'm squaring the r, which gives me r squared. I'm squaring radical 2, which gives me 2, and I'm also squaring 2, which gives me 4. And this is basically the square root of r squared minus 1/2 r squared, which is the square root of 1/2 r squared, which is r over radical 2, which of course is the same thing as x. So come back here and we'll say y is also equal to r radical 2 over 2. So what are the dimensions? Let's see. Find the area of the largest rectangle. So these are the dimensions. Now, what would that area be? Well, remember what we said area was at the beginning. I'll remind you here, area was equal to 2x times y. So in this case, that's going to be 2 times x, which is r radical 2 over 2, times y, which is also r radical 2 over 2. And if we multiply this out, what we get here is the area is equal to r times r, which is r squared. Radical 2 times radical 2 is 2, and then divided by 2. And so the area, interestingly enough, is r squared. So that would be the maximum possible area that we could get from this rectangle. In our next example, we want to find the point on the graph of the hyperbola x times y equals 8 that is closest to the point 3, 0. And I have a graph here just for reference so you can understand what it is we're trying to do. So here is the point 3, 0, and here is the graph of x times y is equal to 8. So somewhere on this graph, there is a point that is closest to this point. So clearly the point is not going to be over here on this curve. From the looks of it, the closest point on this curve to this point is somewhere in here, right? There seems to be a point here that we'll call point P, and we'll give that coordinates x, y, such that this distance between point P and point Q, which we'll call the point 3, 0, this distance needs to be a minimum. Okay, so closest means minimum distance. So again, it's very important that you realize what is it that you are trying to either minimize or maximize in these problems. So if we want to find the minimum distance, we need to know what does the distance between these 2 points equal. So I'm going to call that d, and we're going to remember the distance formula that says if you want to find the distance between 2 points, you are going to subtract the x value minus the other x value, so that's going to be x minus 3, and then squared, plus, and then you're going to take the y value minus the y value, so y minus 0, and also square it. And so our distance is the square root of x minus 3 squared plus y squared, right? Because y minus 0 is just y. This is the function that we are trying to minimize. But again, we have a problem. The problem is this function has two variables. We cannot have two variables. So what else do we know about x and y? Well, x and y represent the coordinates of the point P that is on this curve. And any point that is on this curve must satisfy the equation for that curve. So what else we know is x times y must be equal to 8. And that means y must be equal to 8 divided by x. And so because of this, I can substitute 8 divided by x in for y. And now our distance becomes the square root of x minus 3 squared plus 8 divided by x, quantity squared. And if you multiply this out, you get the square root of x squared minus 6x plus 9 plus 64 divided by x squared. So this is the function that we are now trying to minimize. But we have a cool technique that we can use here. If you wish to minimize or maximize the square root of some function f of x, you only need to minimize or maximize f of x. Now think about this for a minute. If you want the square root of f of x to be as small as possible, then you need f of x to be as small as possible. And the same thing is true if you want it to be as large as possible. So the very nice thing about this is that if I want to minimize the square root of this function, it is good enough to simply minimize the function on the inside. So here is that function. We want to minimize this. So to minimize it, we will take the derivative. So the derivative of x squared is 2x, minus the derivative of 6x is 6. Of course, the derivative of 9 is 0. And then what is the derivative of 64 over x squared? Well, let's remember that it's really 64x to the negative 2. And so the derivative is going to be negative 2 times 64, which is negative 128, x to the negative 3. So if I say that differently, it's going to be negative 128 divided by x cubed. And I'm going to set this equal to 0 to find the value of x that will minimize this function. Now, to solve this equation, what I'm going to do actually is multiply both sides by x cubed. So x cubed times 2x is 2x to the fourth, minus 6 times x cubed is 6x cubed. And then when you multiply x cubed times this, you just get negative 128. That's the whole reason we did it. And then 0 times x cubed is 0. And then I can divide both sides by 2. So that will give us x to the fourth minus 3x cubed minus 64 is equal to 0. And now we have to solve this equation. And this equation is not necessarily easy to solve because it is a fourth degree equation. So there are techniques that you learn in algebra using synthetic division and things like that to find the solution here. In this case, I'm just going to point out that the solution is obviously x equals 4. Now the reason for this, just real quick to justify my answer here, is that I can use synthetic division with the number 4. We have 1x to the fourth, negative 3x cubed, 0x squared, 0x, and negative 64. And I choose 4 because 4 is a factor of 64. And let's go through the synthetic division process. 4 times 1 is 4. Adding, we get 1. 4 times 1 is 4. Adding, we get 4. 4 times 4 is 16. Adding, we get 16. And 4 times 16 is 64. And this gives us a remainder of 0. Okay? So what that means is that x cubed x to the fourth minus 3x cubed minus 64 can be factored into x minus 4 times x cubed plus x squared plus 4x plus 16. Okay? So, bottom line is x equals 4 is the solution. And now we're going to answer the question. The question is, find the point on the hyperbola that is closest to the point 3, 0. So if we know now that x equals 4, y is equal to 8 divided by x. So that's 8 divided by 4, which is 2. And so the point on the hyperbola that is closest is the point 4, 2. Okay? So this point right here on the curve that is closest is the point 4, 2. And if you look at it, I mean, that seems plausible, right? All right. In our final example, we have a rectangular storage container without a lid is to have a volume of 10 cubic meters. The length of its base is twice the width. Materials for the base cost $7.50 per square meter. Material for the sides costs $8 per square meter. Find the cost of the materials for the least expensive such container. So first of all, we need to understand that a rectangular storage container is simply a box. So let's draw a box. And in this case, they tell us that the length of its base is twice the width. So let me say that this is the width here, x, so that's the distance from here to here. The length of its base will be twice that, so that's going to be 2x. And then the height of the box, we don't know what that is. I'm just going to call that h. Now, we are trying to find the least expensive such container. That means we want to minimize the cost. That's what we are trying to do. So what we need is a cost function. How much does it cost to buy materials for this box? So we have to break that up into two parts. We need to find the cost of making the base, and then we need to find the cost for making the sides. So the base is right here, and we know the area of that base is equal to x times 2x, which is 2x squared. So what is the cost of the base going to be? The cost is going to be the area of the base multiplied by the cost per square meter. So it's $7.50 multiplied by 2x squared. Now, what is the area of the sides? Well, this is a little bit trickier because we have 4 sides. We have one side here. We have an equal side across from it over here. And then we have a side here and also a side here. So let's start with this side. The area of this side is 2x times h, but then there are 2 of them, so we have to multiply that by 2. So it's 2x times h multiplied by 2, plus the area of this side is x times h, right? Because the height here is just h. So the area of this rectangle is x times h, but then there are also 2 of those. So it's going to be x times h and then times 2. And so this is 4xh plus 2xh, which is 6xh. That's the area of the sides. So then the cost of the sides is going to be the cost per square meter, which is $8, multiplied by that area, 6xh. So the total cost for making the box is going to be the cost of the base. Let's go ahead and multiply this out. 7.5 times 2 is 15. So that is 15x squared. And 8 times 6xh is 48xh. So the total cost is 15x squared plus 48xh. And to me, this is the most challenging part of this problem. So let's save this, and we'll come back to it in just a minute. So the next step, of course, is to realize that our cost function has two variables, and this is not okay. We have an x and we have an h, and so we have to ask ourselves, what else do we know about this box? We know the volume is 10 cubic meters, and the volume of a box, which I'm going to call V, is pretty simple. It is the width times the length times the height. So it is x times 2x times h, which can be simplified to be 2x squared h. But we also know that the volume in this case is 10. So 10 must be equal to 2x squared h. And if I divide both sides by 2x squared, I get h is equal to 5 over x squared. Right? So all I'm doing here is simplifying. H is equal to 5 over x squared. And because now we know h is equal to this quantity, we can substitute this into our cost function. So now our cost function, which I'll just call C for cost, is 15x squared plus 48 times x times h, which is 5 divided by x squared. Let's simplify this. We have 15x squared plus 48 times 5 is 240. And then this is going to be over x because this x here cancels out one of those x's. And now to minimize this cost, we will take the derivative of the cost with respect to x. This gives us 30x minus 240 over x squared. And we'll set this equal to 0, which means 30x must be equal to 240 over x squared. And then we'll cross multiply, giving us 30x cubed equals 240. Divide both sides by 30, we get x cubed is equal to 8. And then taking the cube root, we get x must be 2. So let's go back to what the question was. It says you want to find the cost for the least expensive container. So we know our cost function is right here. And now we know x equals 2 gives us our least cost. So the least actual cost to make this box is going to be 15 times 2 squared plus 240 divided by 2. If we do the math here, this is 15 times 4, which is 60, plus 120, and that is going to be $180. So the cheapest box that you can make that satisfies the requirements here is a box that will cost $180. And that concludes this video lesson.